So two cars start moving from the same point. There it is. One travels south at 60 miles per hour, and the other travels west at 25 miles per hour. At what rate is the distance between the cars? At what rate is the distance between the cars increasing 2 hours later? So they are asking us to find dc dt, where c is the hypotenuse of this right triangle. And I'll make this side, I'll call it variable A, and I'll call the length of this side variable B. So we know that dA dt is growing, that distance is growing at 25 miles per hour. dB dt is also growing. It is growing at 60 miles per hour. I need an equation that relates these three variables that I have rates for, and that's going to be a Pythagorean theorem. So I end up with a squared plus b squared equals c squared. Once I have the equation, then it's time to take the derivative with respect to time. Make sure you are differentiating implicitly with respect to time. And 2 times blah times the derivative of blah with respect to time. And once I have taken the derivative with respect to time, then I'm going to plug and chug. We know dA dt is 25. We know that dB dt, see if I can write that a little bit better. Stop. We know that dB dt is 60, and we are being asked to find dC dt. We need to know A, B, and C with the when information. The when is 2 hours later. So 2 hours later, A is going to be 50 miles, and B is going to be 120 miles. And then I need to Pythagorean theorem and get the C value. And I'm going to check that Pythagorean theorem real quick. You may want to fast forward right now. And 130. That should not have taken me that long. Okay. So now that we have A is equal to 50 and B is equal to 120 and C is equal to 130. And I'm also going to save myself a little bit of breath and divide by 2 all across the board. And I can also save myself a little bit by dividing by 10 to each term. And let's see what we get for dC dt. we have 25 times 5. And then plus 12 times 60. And then that is divided by 13. So 845 divided by 13. And I get 65. So the distance between them is growing at a rate of 65 miles per hour. Next problem, number 23. The infamous conical tank. An inverted conical tank will take on this shape. And we have water is leaking. Water is leaking out at 10,000 cubic centimeters per minute. At the same time, water is being pumped into the tank at a constant rate. Let's say that that constant rate is C. That means that the rate of change of volume with respect to time is whatever constant it's being pumped in minus the 10,000 cubic centimeters per minute that we are losing. And it wants to know find the rate at which water is being pumped into the tank. So in other words, we're trying to find C. So they must have given us some more information about a rate of change. The water level is rising at a rate of 20 centimeters per minute. And this one was cubic centimeters per minute. And there's our water, height, and a radius. Okay, now we are told that the diameter of this tank is 4 meters. The height of the tank is 2 meters. Nope. Height of the tank is 6 meters. That gives us a ratio because the water cone and the tank cone are similar, so they have the same ratios. That gives us that R is to H, as the radius, which is 2, is to the height 6. Now we need that because the volume formula of our cone is 1/3 pi r squared h. We are working with the rate of change of volume, and we are working with the rate of change of height, but we have no given information about the rate of change of radius. So we are trying to find out what is the radius in terms of the other variables. And we get that it is 1/3 h, so I'm going to plug a 1/3 h into that r. And that is going to give me volume is 1/3 pi times 1/3 squared times h squared times another h. And then I'm going to simplify that just a touch more. And now we are ready to take the derivative with respect to time. dv dt equals constant multiple, and then I chain rule 3 blah squared times the derivative of blah with respect to time. And now I'm ready for the plug and chug moment. dv dt is constant minus 10,000. And that constant is what we are trying to find. dH dt is 20 centimeters per minute. and I need to look at the given information. The given information is when the height of the water is 2 meters. Careful, careful, because our rates of change are based on centimeters. I need to make sure my height is in terms of centimeters. So if it is a height of 2 meters, then 200 centimeters is what h is equal to. And now it is time to simplify the math. I'm going to grab a calculator. I'm going to keep the pi going. And I have 3 divided by 27 is actually going to give me 8 divided by 9. I guess I'm not using a calculator. And then I have 4 times 3 is 12 and 3 zeros. And finally, the constant is equal to 12,000 pi divided by 9 plus 10,000, provided I didn't make any arithmetic mistakes. There it is. Next problem is number 27, and it's another cone problem. It wants to know how fast is the height of the pile increasing So we will be finding the h dt. And we've got our when information that we'll hold off on. We are told gravel is being dumped from a conveyor belt at a rate of 30 cubic feet per minute. So that means my volume is increasing by 30 cubic feet per minute. And these are my rates of change that I need to work with. So just like before, I have the formula for volume of a cone is 1/3 pi r squared h. But I'm only working with rates of change for the volume and the height. So I need to figure out what is the radius in terms of the other variables. Now, we were told that this magical pile has the base diameter equal to the height. So that means that the radius is equal to half of the height, and I will plug that into the R. Then my volume is going to be 1/3 pi times 1/4 as I square the 1/2 times h squared times another h. And I'll simplify the volume a little bit more, pi over 12 times h cubed. And then I take the derivative with respect to time. That gives me dv dt equals constant multiple times, and then I'm chain ruling. Blah cubed derivative is 3 blah squared times the derivative of the blah with respect to time. Once I have that done, it's plug and chug time again. And I know that dv dt is 30. And I'm trying to find dh dt. The only thing I have yet to find out is what is the h for the when information. When the pile is 10 feet high, there is my h. So now I have 30 equals pi over 12 times 300 as I square that 10 times dh dt. And then when I divide the 30 by the 300, I just really want to do that division. That's going to leave me with 10. How about I do that? And ultimately, that will then be 12 divided by 10 pi, which would then reduce to 6 over 5 pi. So that is the rate at which the height of the pile is changing. All right, now we have a magical kite that flies horizontally as we let out the string. So my kite flying horizontally at a speed of 8 feet per second. What is its distance above the ground? Its distance stays exactly 100 feet. And then I've got the string being let out. So we're imagining someone's actually laying down on the ground with the string in their hand while the magical kite is flying horizontally. The when information we want to wait on, and we have a given rate. They want us to find the rate at which the angle between the string and the horizontal, that would be this angle right here. I'll call that theta. We want to know the rate at which that angle is decreasing. We need to find d theta dt. And I need to choose a variable for this horizontal distance. Let's call it x. That horizontal distance is growing, so it's positive 8 feet per second. When I create my equation, I want to make sure that x and theta are involved. Anytime an angle in a right triangle is being asked for its rate of change or it's given as a rate of change, and you have a right triangle again, you are using any of your 6 trig functions, which means you are using only 2 of the 3 sides of this triangle. Now we have to use x. And then the wise thing to use is the side that's constant. That will end up being less work. Also, I will have the least amount of work if I create an equation where x is the numerator and the constant is the denominator. If I do that, then I have adjacent over opposite, which means I have cotangent. But that's going to save me dealing with a quotient rule or a -1 exponent. Worth it. Now we take the derivative with respect to time. For cotangent, the derivative is negative cosecant squared. And remember, with respect to time, so give mommy her baby, theta, and then times d theta dt. Constant multiple 1 over 100. Make your life easier. Realize x over 100 is a constant times x. And we are differentiating with respect to time. So that constant times dx dt. Also with these problems, don't go and try to figure out what theta is. You want to figure out what the two-sided ratio is. Now, cosecant is the reciprocal of sine. Sine is opposite over hypotenuse. So that means this is hypotenuse over opposite. And we need to find the hypotenuse. That'll be our when information. When 200 feet of string have been let out, there's our hypotenuse. We are trying to find d theta dt. And dx dt is 8. This gives me d theta dt being equal to, and I'm just going to reduce this thing to a 4. That's 2, 2 squared 4, so negative 4. I'm going to be dividing 8 over 100 by negative 4. And I will end up with negative 1 over 50. And that's feet. Nope, nope, nope. Theta, theta. The units are radians per second. That is how quickly theta is decreasing. So you would say that that angle is decreasing at positive 1 over 150 radians per second. Next problem, television camera rocket. So a rocket is being launched. I'm going to say that that point right there represents the rocket heading upward. And you have a camera that is positioned horizontally 4,000 feet away from the base. So there's my camera. And the angle of elevation of the camera has to change. That's going to be involved in part B. So I'll wait on that. But I will draw my right triangle. Let's see what we are given for rates of change. We are given 600 feet per second is how fast the rocket is rising, because it's a magic rocket and it is moving at a constant speed. And we are being asked to find in part A, how fast is the distance from the television camera to the rocket changing? So that's going to be this hypotenuse. We want to find the rate of change of that hypotenuse. So how about we call that h for hypotenuse, and we'll call this changing vertical distance y because it's vertical. And in part A, I am not dealing with any angles. I am being asked to find the h dt while knowing that dy dt is 600. So when I look at the rates that I'm expected to create, those variables h and y need to be put into an equation. Again, notice no angles are chosen here. And if you take a good look at this triangle, woo, Pythagorean theorem, here we come. So 4,000 squared plus y squared equals h squared. Taking the derivative with respect to time, for the constant we get 0. And then 2 blah times the derivative of blah with respect to time, and 2 blah times the derivative of blah with respect to time. Save myself a little bit by canceling those 2's, and it's plug and chug time. dy dt is 600. We want to find dh dt, and now I need my when information. When it has risen 3,000 feet. So when this vertical y is 3,000. And that kindly gives me a 3-4-5 ratio. And now I can plug into the y, 3,000. I can plug into the h, 5,000. And before I go calculating, I'm going to make my life easier by dividing both sides of the equation by 1,000. And now I have 3 times 600 gives me 1,800 divided by 5. and that gives me dH/dt. You can do the division by 5. All right. Part B, now we're looking at how fast is the camera's angle of elevation changing at that same moment. So I'm going to put down d theta dt equals question mark. We did find dH/dt. If we want, we could use it. So angle of elevation is always from a horizontal looking upward. So this is our theta. If it was angle of depression, that's always horizontal looking downward. Now, if I'm dealing with a right triangle and a rate of change that is one of the two acute angles in that right triangle, you are trying to decide what two sides are you going to put in a ratio and turn into a trig function. Now, we were given the rate of change of the vertical side. We have a constant side. That would be really nice to use. But we could, since we know dH/dt, we can use any trig function we want. I'm going to go with using the y that we were given. So if I make an equation, I want the variable to be the numerator and the constant to be the denominator to make the derivative easier. For this angle, that means opposite over adjacent, and it's tangent theta. Now we are ready to take the derivative with respect to time. Remember, this is a constant multiple 1 over 4,000 times y, derivative with respect to time, dy dt. Tangent theta, derivative of tangent theta is secant squared theta, but we are chain ruling, so we give mommy her theta baby and multiply by the derivative of theta with respect to time. And now plug and chug. Dy dt is 600. We want to find d theta dt. We need to know secant squared. Secant is cosine's reciprocal. With cosine's reciprocal, we are looking at hypotenuse divided by adjacent. So 5,000 over 4,000, or 5/4 as a ratio. And then a little bit of make the fraction simpler. And let's see, 3 and 20. So we have 3 divided by 20 times 4 squared over 5 squared equals d theta dt. I can simplify a little bit here, divide by 2 again. And now I have 12 over 125. That is my d theta dt. It's a positive rate of change, and that makes sense with the problem. The angle is increasing, and the units on it are radians per whatever the unit of time was, seconds. Okay, then did I have another problem, or was that my last one? That was my last one. Woohoo! Got through all of them. I will see you online.